Hi, this video is going to finish our coverage of the linked list operations. So remember that 2 videos ago we defined what a singly linked list is. The previous video went over all of the constant time operations, and what remains is this video that goes over the linear time operations. These are operations that need a loop or maybe recursion to repeat something. That includes the index-based operations, get I, set I. Based on an index, you need to skip over node pointers, and also the PopBack operation. Now, why does PopBack take linear time when PopFront takes constant time? Well, it has to do with the fact that we have a singly linked list, and those single links only go forwards toward higher indices. So when we were trying to pop the front, we needed to get to the first node, and the first node is always tails next next. So you could follow 3 pointers to get from the list object to the first node. It's always 3. So we didn't need a loop, we could just follow 3 pointers. Well, when we do PopBack instead, we're trying to remove the last node, and there's no direct way of getting that in a constant number of pointers. Here's the issue. What a computer algorithm can do is start from the list object and follow these arrows. We need to follow arrows to get to the second to last node. Why do we need the second to last node? Well, because things need to be updated relevant to the second to last node. The invariant on the singly linked list is that the last node's next needs to point at the dummy node. So on the right here, I have a sketch of the 714 list after removing the last node. The 4 goes away and the 1 becomes the last node, so the 1's next needs to point at the dummy. So I need to get to this 1 node to change its next pointer. Also, 1 becomes the last node, so I need to change the tail pointer to point at node 1. So for 2 reasons, I need to get a pointer to node 1. Well, as a human, I can kind of glance at the last node and look to the left, but a computer can't do that. It has to follow these pointer arrows. And the only way that I can see to get to the second to last node is to follow the tail. And it's going to be kind of slow, but we just got to do it. We got to wrap around to the beginning and go all the way until we get to the second to last node and stop before we end up at the tail again. And in a long list, that means skipping over practically every node. That creates a linear time loop. So PopBack needs a loop to do this kind of slow process of skipping over all of the nodes to get to the second to last node that takes on the role of the last node. Okay, so the 3 remaining operations of PopBack we were just talking about, and get and set based on index, all will involve this skipping over nodes operation. So rather than repeat that 3 times, I'm going to make that its own private helper function. So this operation, what it's going to do is start from the dummy node to the left of the first element and skip over a given number of nodes. We're going to make this a private helper function. This would not be public because the user of our list shouldn't need to know about these internal details. Here's how the function works. I'm calling it skip. It's given an index I as a size t, and it returns a pointer to the node at index I. Now this indexing system starts at the dummy node. It's a little detail. So dummy is I0. The first node that has an element would be index 1. The second node that has an element would be index 2. And the third node that has an element would be index 1. Note that we're off by 1 from what the end user would see, which is that 7 is at index 0, 1 is at index 1, and 4 is at index 2. So that's a detail we'll address in a moment. How the code works is I have this pointer I call where, and to begin with it points at the dummy node. That's the definition of what skip does. How do we get to the dummy node? The dummy is always tails next. So follow tail, follow the next. Now where is pointing at the dummy node. And then I have a conventional loop that repeats I times, j equals 0, j is less than I, j plus plus. And each one of those times where becomes where's next. So if I want to go to index number 2, then where starts off pointing at dummy, and then I repeat 2 times, go to the next, and now I'm at index number 2, starting from dummy. And we return a pointer to that node as the return value of the skip function. Skip is a linear time function because this loop repeats, obviously, and in the worst case, I is the size of the list, and so this loop repeats n times, takes constant time per iteration, so this is a linear time operation, and this is the source of the linear time performance of the remaining operations. Now let's get into the details of these 3 operations. First, get index I. Here's my algorithm. First, I just check I to see if it's an illegal index and throw an exception if it is. It's not hard, but we need to do that. Then we skip to node number I plus 1. Note that it's not node I. That's because, remember, we are counting in the skip function the dummy as index 0, but the end user thinks the first element is at index 0, so we have to account for that discrepancy. We know we have to skip over the dummy node. We don't want our caller to have to worry about that internal implementation detail. So here's the code. Get takes a size t index I, it returns a t. If I is greater than or equal to size, throw an exception. If we get past that, we skip to index I plus 1. That returns a pointer pointing at the node object that has the element the user wants, and we return that pointer's element. Takes linear time, and the bottleneck is the skip function call. Set index I to value x is very similar. The difference is once we get the pointer to the node that we care about, instead of returning the element there, we assign the element there. So this is pretty similar. We have an index check, skip to node I plus 1, and then call the mutator on the node object. So set is given an index I, a tx. If I is out of range, throw an exception. Otherwise, skip to index I plus 1, and that pointer sets its element to x. Linear time, and the bottleneck again is the skip function. Finally, PopBack. So this one's a little bit more complicated because we need to change the node pointers. Here's the algorithm. First, throw an exception if the list is empty. You can't remove the back element if the list is empty. Otherwise, skip to node size minus 1. Okay, that's the second to last element that contains or second to last node that contains an element. So let's just check my arithmetic here. Let's say I want to pop back on this list. Well, that means I want to remove the node containing 4. In order to do that, I need to get to the second to last node that contains 1. So I need to jump to this 1. How many hops do I need to do? Well, if I started at the dummy, I need to go 1, 2 to get there. And that's the size minus 1. So we're going to skip to node number size minus 1, and then remove the node to the right of that. So node at index size minus 1 is the second to last node. We remove the last node, which comes next. We need to update the tail pointer because we're definitely changing the tail. The last node goes away and becomes this second to last element. And update the size minus minus. Don't want to forget that detail. This is going to end up taking linear time, and the bottleneck is the skip step. All of the rest of this takes constant time. Here's what code would look like for this. So if the size is 0, then throw an exception. It's empty. Otherwise, before target is skip to index size minus 1. So if I'm popping back on this example, size minus 1 is 2, and so before target would point at the second to last node, which is the 1, and then target would be the node after that. So target equals before target next. Target is the node I'm trying to get. I'm targeting it for removal. Before target, set your next to target next. So 1 needs to change its next pointer to point to whatever 4's next currently is, which will actually always be the dummy node. And then the tail needs to move to before target. So currently tail is at target, tail needs to move to before target. Minus minus size decrements that to 2. Let's look at a couple examples. First, let's look at the common case of a multi-element list where there's 2 or more elements. We'll use our 3-element list here. First, we check if the size is 0. It's not, so we skip past that. Before target points at the index number 2, counting from the dummy, which would be node 1. Then target points at the next node of that, which is the last node containing 4. Before target changes its next pointer to target's next. So that updates this red pointer to point to the dummy node because 1 is getting ready to be the last node. Then the tail is assigned to before target. That updates the tail pointer. Finally, size decrements to 2, which is accurate. And there's some kind of leftover garbage here. When we get to the end of the function, that all gets freed automatically. What happens is, if you notice, we've got shared pointers to node 1 and node 4. The before target shared pointer goes out of scope and it's destroyed, but there's still incoming pointers to node 1, so this one object does not get freed. When we remove the target pointer to node 4, that's the last pointer to 4, and at that point there are no incoming pointers to 4, and the shared pointer class knows that 4 should be deleted right now, and 4 gets deleted automatically for us, and we don't need to write code for that. So this is the strength of smart pointers and RAII. We don't need to worry about freeing that 4 node, it just happens implicitly for us. Let's go through the same kind of example, but now in the special case of starting with a list with only one element. Let's double check this code works in that case. So to begin with, if the size is empty, throw an exception. It's not because size is 1. So before target is skip to size minus 1. Size minus 1 is 0. So skip 0 just points us to the dummy node. So before target is the dummy node, which is right. It's the node that comes before the one that is targeted for removal. Target is the next of that, which holds the 7. It's the only element carrying node. Before target, set your next to target next. Okay, so before target, next pointer becomes target next. Target's next is the dummy, so it's a little bit complicated, but dummy's next becomes a pointer to dummy itself, and that's correct because an empty list should have the dummy node pointing at itself. Tail points at before target, which is the dummy node, and that's correct. Size minus minus, size gets decremented from 1 to 0. And then again, when the pointers go out of scope, that last node gets removed, and we're left with just a correct empty singly linked list. Okay, to summarize, here are the operations of the singly linked list. There are a bunch that take constant time because there's no looping involved. So that's creating an empty linked list, getting the size of the list, getting the front element, getting the last element called the back, adding to the front called push back take constant time, pop front, removing from the front. So those common operations are all constant time, very fast, and no amortized because unlike the vector, there's no resizing or copying. However, PopBack takes linear time. That's because in order to remove the last node, we need to get a pointer to the second to last node, and that involves skipping n-1 nodes. And then get I and set I. So getting and setting by index takes linear time because, again, you have to skip over a bunch of nodes, and that's one thing that makes a vector appealing. Vectors can set and get by index in constant time.